All right, I'm recording it. So put your answer in the chat. Tell me conceptually, why does the current go down in my circuit over time? Okay. Put it in the chat. Okay. Energy does start to change form. That is true. But think about what's happening in the capacitor. That's really the key point. I'm gonna plot this here. I'm gonna change my constant. I'll keep this 50, and then I'm gonna plot another one. I'm gonna make this constant bigger here. Oh, so if I make R over C bigger, it takes longer for the current to go down. Okay. All right. So it's okay if you don't know. Let me, in a minute, we're going to actually build this circuit and turn it on and see what happens. And we'll make some observations from the circuits, because it's always better if you make your own observations. Don't take my word for it. Convince yourself. All right. There we go. Okay. So I think everybody has put their answer into the chat. All right, we have our equation here that shows current is going to decrease over time. But let's go to the circuit now and see what happens when we turn this sucker on. Okay, so we got our circuit here. Let's actually build our circuit. I need to turn up the lights. Dr. Wisby, I can't see anything. Okay, there we go. All right. Got a lot of buttons here I can push on all my gadgetry. Okay, so we got our little circuit here. What we're gonna do is we're gonna hook it up to our power supply right here. So let me disconnect that. And I'm gonna hook up one side of my battery here, the positive side. I'm gonna get a banana cable. Hey, here's our banana cable. We're gonna plug it into the plus. Yes, we're gonna plug it into the plus. It actually kind of doesn't matter which way you do it. So we got this connected over here to our capacitor. The other side of the capacitor, my cables are really long, right? I'm gonna plug in over here. So we're going from our power supply to the capacitor, from the capacitor over to here. Then it's gonna go into this resistor. It'll go through the resistor, and then the other end of this thing, one other important element I got here, I have a current meter. Yes, well, we can see the current here, what it's going to be. Okay, so remember, if you want to make a current measurement, and we definitely do. Now we're going to go from over here into our current meter right there. There we go. Okay, and then from the other side of our current meter, now we're going to plug this back into, and look, it already started. See, that thing is glowing. Look at that. My LED has turned on, and look at my current here. It is starting to decrease. I'm going to go, this were in milliamps. I'm going to go to microamps. Okay, so we've got minus 22 microamps, and yes, it looks like the current is decreasing over time. So and if you'll notice that the LED has gone out here, okay, and we'll talk about why. That's because you need enough current in your diode, okay? And if the potential difference between my power supply here and my capacitor is not big enough, then this thing is not going to go on, okay? And I should have been timing this, but I did not. But this is taking a while here to charge up my capacitor. So we're we're going on a couple seconds. That's because this is a pretty big capacitor over here. So what's going on in the circuit is that we are loading this thing up with current, right? And as we get more and more current, then our capacitor is going to become full. Once our capacitor fills up, current is going to stop flowing. Okay, no more current will flow in the circuits, and it will basically completely shut off. Okay, so we're still on the tail end of that exponential curve. Let me share my screen with you. If we go back to our plot here, so now we're like over here. We're in a very, very small amount of current. We're on the tail end here. Okay, so this thing is it's barely going. We're way, way over here. Okay, so this is charging our capacitor. So this thing is gonna take some time to do that. All right, so we did the charging. Now let's go to because now we're gonna discharge this thing. Okay. Okay, so we're still charging up. All right, so now let's talk about what happens when we discharge this thing. And I'm kind of running out of room here. I'm gonna have to move my little circuit over here so I can draw some stuff. Okay, so now, well, let's just watch, since we've got this thing hooked up here, let's watch what happens when we discharge it. I'm gonna disconnect my power supply here. My capacitor is not fully charged, so my circuit is not complete right now. So this is like I broke the switch on my capacitor, so it's just in an open state. So I didn't actually have a little toggle switch, but I did disconnect these two things from my capacitor. And over here, the last time this LED was on, now when I connect these two, we're gonna see that the other LED comes on. I'm gonna plug this in here and watch what happens to the current as well too. Okay, so, oh, now we've got a big current. We were in milliamps, okay, so we're 1 milliamp. The LED is on, but it's slowly going off. Okay, so the light is going out here on my LED. Okay, and now I'm going to switch to microamps. Okay, so now I've got 28 microamps. All right, and it's taking a while for this thing to discharge. Okay, so now basically this thing is acting like a battery. It's supplying current to my circuit. You can't see the LED anymore because the voltage here has dropped significantly. There's not a lot of current here. This isn't enough current or enough voltage to light the LED, but this circuit is still discharging. So even though my LED is not on, current's still flowing. I can measure it here, but it's taking an exponentially long amount of time. Okay, so I'm gonna let this thing go. I'm gonna move my circuit over here. We can continue watching the numbers, but now I'm going to move my power supply out of the way, and I'm gonna, oh, so I will keep my power supply, keep my voltage meter over here, but now I'll have some more room to write. Okay, there we go. All right, so let's talk about what happens when you discharge this thing. There we go. There's my meter. Well, when I discharge it, now I'm gonna have the charge on my capacitor as it's being discharged will equal Q times Q0 times e to the minus t over RC. And this quantity RC, that is a very, very special quantity. It's called the RC time constant. And usually we write that as tau. So we'll say tau equals R times C. Okay. Now, if we wanted to, yeah. Right. Now, if we wanted to know what the potential was across the battery when it was charging, okay, we know that Q equals, well, we'll have Q divided by C. That gives us voltage. And then this will be E times 1 minus E to the minus T over RC. Okay, so this is the EMF supplied by my power source. And this is the potential that I would experience across the two terminals of my capacitor. So right here. Okay, so the V would be the potential across here, which is different than your power supply. Okay, and I'm still discharging, my circuit's still running, so I still have a little bit of current in my circuit. Okay, and if I want to know what my current is here, now I'm going to take the derivative of this with respect to time. So I'll have dq over dt, and then that's going to be q0. The derivative of E is E to the minus T over RC. This part doesn't change, but now I'll get a times a minus 1 over RC. All right, so I had a minus sign there. It goes right there. So now I'll have that my current is equal to Q0 divided by RC times E to the minus T over RC. And then this is negative. Okay, so the negative sign there, that tells you that current is flowing in the opposite direction. And Q0, that's the amount of charge that you stored on your capacitor. So after you fully charge up your capacitor here, QZ is however much charge you put on this thing. Okay, and if we want to know what our voltage is here, okay, so when this thing is discharging, okay, we can divide that by C because we know that V equals Q over C. So if I go right here, now I will have Q0 divided by C times E to the minus T over RC. So the voltage from your capacitor changes over time. Okay, so now somebody said, does the current go down because energy gets lost as heat? That's a good question. You do lose some energy in your capacitor. So when you're charging this thing, it's not 100% efficient. Okay, so as you're charging it, you do lose some energy resistively to heat. Okay, so you've got a resistor in there, so some of your energy is lost. But the reason that it starts that the current stops flowing is because once your battery or your capacitor has the same potential difference as your power source, you can't draw any more current, because then the power supply and your capacitor are at equal potential. That means current cannot flow any longer. So basically the reason is your capacitor fills up. It's full of charge. Then current stops flowing. And then when you discharge it, you can discharge current for as long as there's still charge on your capacitor. Okay, so could we use capacitors as a battery? That's a little bit complicated because what you ideally want in, say, an electronic source is you want something that is going to supply a constant voltage. Okay, now a battery can keep its potential. So this is about 1.2 volts. That doesn't change a lot the whole time that you're using the battery. Okay, so my capacitor, our current is really low. Whereas a capacitor, the voltage in this starts to change right away. So a battery is different because it's designed in a way so that it can always supply close to 1.2 volts or whatever it was set at for all time. It doesn't change. It's what we call a stiff power supply. So in your computer, or your phone, those digital circuits are usually powered by maybe 1.5 volts or maybe 0.7 volts. You need to maintain that constant voltage for all of the circuits to work. So using just a simple capacitor is not the way to go. Batteries are nice because there's a chemical process in your battery, and as long as there's still some reaction that's available. So if all of the chemicals haven't combined or the reaction isn't totally finished, it will always give you 1.2 volts. So that's pretty good. Now, when I was watching the news today, because I have been transfixed to the TV, as maybe some of you have, maybe not, I saw something that gave me hope for America. And let me put it on the screen here. And I was totally blown away. And I think, oh, let me share this with you. I thought, you know what? No matter what happens in our election, there's still hope because of this new invention from GMC. Let me play this for you. And you don't read the title there, but let's watch this commercial. Revolutionaries. Guess what it is, everybody? Ones that changed the game forever. Yes, very American commercial. It's a big truck, not like the old trucks, because seeing the world not as better. It's a vision of how it could be. A new America. That's how true greatness is. There it is. Look at that. Wow, guys. It is an electric Hummer. Oh my gosh, it's amazing. I want to buy one. Why not have electric Hummers? It's the best of both worlds. You can have a giant SUV and it's all electric. Yes, we've finally done it. Now, here's a question for you. Not to, so when I saw this, I was like, oh my gosh, it's an electric Hummer. Wow, GMC has finally done it. GMC also has a whole line of all electric cars, which is great. I'm totally for that. But here's the question, guys. Okay, so you make this this monstrous electric vehicle. Is it good for the environment? What do you think? Is it what's it going to do for your carbon footprint? So let's say you're thinking, all right, let me get a really majestic picture of this amazing Hummer. Oh, there, look at these mountains. Oh, through the desert. Okay, is this going to be good for the environment? And let's have a little discussion here in the chat. Okay, I'll give you points for this. Yeah, that's not very. So is it good for the environment? Right? You're still going to have to get energy to power this thing. Where are you going to get your energy from for your Hummer? So yeah, good comment there. It might just switch your energy source from gas to coal. That could be true. So, okay, now maybe we're not burning, we're not using gas, but now we're using coal. Okay, is that what's that going to do for your carbon footprint? Is that going to decrease it? Because now we know that electric cars are more efficient. So, once you get the battery in there, let's see. It will help our footprint in that you are using electric, but still could be using coal. Yeah, that's true. It is electric. You're still going to be using coal. There's a good point. Somebody said that there's also the manufacturing cost. Okay, so to build these electric Hummers, which are totally awesome, I think nobody would question that. But we know that the batteries take a huge amount of energy. And I'm just guessing, I haven't looked at the stats, but compared to a Prius, you're going to need a bigger battery, to really to power your new electric urban assault vehicle. So there's going to be a cost for making the battery. Let's see what else you guys are saying. I think it depends on what resource is going to making the Hummer. Okay, so that's true. Because if you're trying to think about, all right, what is my carbon footprint for the entire vehicle? How much energy is it going to cost to make this thing? Yeah, so what's the total carbon footprint of the car? Well, that's that's a good. Somebody said, well, how far along in the production chain of the vehicle are we thinking about? Are we talking about from when you go and mine the metal for this, where you get the rare earth elements? How much is that going to take? Because when when we drive a car, if you look at the entire carbon footprint, including when it was manufactured, that's an issue. Which was why originally when the Hummer first came out, of course it was gas powered, and it got, I don't know, maybe 5 miles per gallon, maybe 10. Let's say it got 10 on the freeway, maybe 15. I think 10. I think a big issue is it's not very aerodynamic. If you're looking at the Hummer, it's got a very big cross-sectional area, which is going to give you a lot of drag. Okay, so somebody said, can we solve for the efficiency with thermodynamics equations? Maybe, but it's still not very aerodynamic, so it's going to take a lot more energy to drive this thing. It's got to have a huge battery, which is also going to cost a lot of energy. But maybe if you could charge this thing with solar panels or a hydroelectric dam, then you're talking about, then you can start getting an energy saving. So down the road, maybe after probably 10 or 11 years of driving this thing, if you're using solar energy, now you're talking about, okay, now we're going to decrease our carbon footprint. We don't have to use gas. And so, yes, I think it, but let's see what other people said. Yes, it probably is better than a normal Hummer. That's true because it doesn't use gas. So over the long haul, you could save energy that way. But it does depend on how much it costs. Okay. All right. Well, that's enough about my new car. They also have electric Harleys. So the electric Harley Davidson, I think, is pretty cool. Oh, what about battery recycling? Ooh, that's that's another question. Okay, so obviously, when you're done with the battery, hopefully you recycle it. But it does have, it's going to have rare earth elements in it, and these are really hard to get. So you would definitely want to recycle it, take and reclaim those minerals. Okay, guys. Well, I think that's it for today. I will put the test online. What is it? Oh, wait. Is there a limited supply of electricity to power these things, or can we produce electricity indefinitely? Well, we're pretty good at making electricity. We've got a lot of coal. We've also got a lot of fracking. So the U.S. has a tremendous supply of natural gas, which we get through fracking. We've become totally energy independent, and that was a big issue in the election. Joe Biden was like, at first he was like, no fracking, we're gonna end fracking, but then they're like, no, I'm not gonna end fracking in Pennsylvania because everybody loves fracking. So energy it's gonna be a big issue going forward, big political issue. There's good things and bad things about fracking. We get lots of natural gas, but natural gas is cleaner than coal. So if we burn it, we'll produce less CO2. But there's also a cost for fracking. If you live in a place where they do fracking, there's a possibility that your groundwater could be contaminated. Everybody likes clean water. So, but all right, guys. Oh, homework questions. Yes, let's look at homework questions. Oh man, I get to talking about electric cars, and look what happened. All right. So let's go look at a homework problem. Let's look at, all right, I think let's look at the last homework problem. That was a good one. I think somebody sent me a question about that. So let's quickly take a look at the homework. All right, I'm logging in, and let's look at one of these problems, and then we'll get started on it. Okay. Chapter 27 homework problems. Let's go to the last one. Wait, let's look at problem 41. Oh, problem 55 if we have time. All right, we'll do problem 55. Oof, that's a good one. Problem 55. Let's take a look at problem 55. Oh, I put the on the screen. Oh, look at that. Okay. In figure RS is to be adjusted in value by moving the sliding contact across it. Yes. The test is assigned later today. And I can go through this problem completely later, and I will have office hours this weekend. Okay, I will find a time to send out to you. Let's start on this problem. One test for this condition is by momentarily connecting a sensitive ammeter and meter between A and B. So this point are the sample potential. The ammeter will not deflect. Okay, so express Rx in terms of RS, R1, and R2 in the case when we adjust this mode. All right, so let me draw a picture of the circuit, and then we will try and diagnose this circuit. All right, and what is the problem asking? So in the figure, RS is to be adjusted in value by moving the sliding contact across it until points in A and B are brought to the same potential. All right, so let's switch to the page. All right, so here's my circuit. Quickly draw it. R1 and R2. Okay, and then I've got another circuit down here, RS, and I've got another circuit over here, RS, but this is on a sliding potential, so here, B, okay, A and B, and then I've got R0 over here, and I've got my battery right here, so this is plus and minus, so plus and minus. Okay, so let's take a look at the current. Okay, so we've got a couple current loops. Okay, so we're gonna have, let's say we're gonna have current going this way. We'll have one current going that way. We'll call it I1. Yeah, we'll call that I1. And then we're also gonna have another current going through here. So this will be I2. All right, now we've got a loop here, and there's no potential in my loop. All right, so if I go across this way in the direction of current, we're gonna say that that's positive. So as I go around the loop here, I will have R1 times I1 plus R2 times I1, my current here. Then as I go around the loop this way, I'm going backwards across. Oh, these should be minus. I'm gonna call that, I'm gonna make those minus. Now I'm gonna go around this way. These ones are gonna be positive, so this will be plus I2 RS and plus I2, and we'll call this RX because we don't know what this is. This is a sliding resistor here. All right, so that's going to be, yeah, so I2 plus RS plus I2 plus RX. And what is the problem asking for? All right, express RX in terms of RS, R1, and R2. Okay, so we've got our equation. We did it by going around our loop here, right? And now I think we can solve for Rx. All right, so let's get this on the other side. So we've got I2, and at this point now, we've basically got this, and it's a bunch of algebra, which we can do. All right, so this will be I2 times Rx. I'll move this over here. This will be R1 times I1 plus R2 times I2. Okay. And now I think you should be able to solve for Rx. Okay, I think at this point we can do it. All right, what else do we need for this? Now, our points here, A and B. All right, so we can go, let's say this way. All right, well, that's all for class now. If you need to go, you can go. I'm gonna stay here and finish doing this problem. So if you'd like to hang out with me and see how to get through this problem, you can. But if you need to go, you are free to go. But I'm gonna keep working this problem. I'm gonna record this, and so it'll be available online later. Thanks for coming to class today, guys. I really appreciate it. And I will see you later. And if you want to stay here, I'm going to finish this problem. So thanks a lot, guys, and I will see you guys later. All right, and I'll send out information about Fortnite. Okay, all right, so let's see. What else do we need for this problem? We want to get everything in terms of R, so we need to solve for I here. Okay, now. All right, so let's see. All right, so A, as we go across here, and then we go across this one, the question says, by moving the sliding contact across it until points A and B are brought to the same potential. Okay, so A and B are going to be at the same potential. That's an important clue. Okay, so then that means that, what does that mean? We'll write, oh yeah, if those are at the same potential, we're gonna have, oh, yes, we can go this way. So we'll have I2, it'll go across here. Oh, but that'll give us, yeah, so we're gonna have R1 and R2. So this has to be at the same potential. All right, so let's move across here. We'll say our voltage drop across there. That's I1 times R1. And that has to equal, if we go across this resistor here. Oh, wait, I drew this wrong. This is RS and RX is over there. Haha. Yeah, RX is over here. Oh, I totally drew that wrong. And RS is over there. All right, so if we go across here, we're going to have a potential drop. And if we go across this thing, we're going to have the same potential drop. So those two are equal, because in our problem, it says A and B are equal. So now we have this. So we can solve for I2, and then we can put this in here, and now we will have everything in terms of I1. All right, so let's do that. So we'll have I2 is going to equal I1 times R1 divided by R2. Okay, so from this expression, that gives us this one. And now we can use that up here. So I need to simplify this expression some more. All right, so let's do that. We want to get this in terms of Rx. So I'm going to come down here. I'll bring this down here. So, yeah. All right. So over here, I'm going to factor out, wait, what did I do here? All right, so this is R1 times I1 and R2 times I1. That's supposed to be a 1 right there. Okay, so over there, we're going to have R1 plus R2. I'm going to factor out my I1 here. So from right up there, got this one. And then up here, I'm going to have I2. So I'll factor out that I2. So I'll have I2 times RS plus RX. And now I know what I2 is here. So I can substitute in I2. So I will have, I'll put in for I2 right there. Now I'll have I1 times R1 divided by R2 times RS plus RX equals R1 plus R2. Oh, we're not supposed to be an X right there. There we go. All right, and this is times I1. All right, well, that's good. So the currents actually will cancel here. So I1 goes away. Now I'm just left with this. So I'm going to multiply both sides by R2 over R1. So R2 over R1. This will cancel, and then I'll have an R2 divided by R1 here. So now I'll have all right, so now I am going to get, I'll get RS plus RX equal to R1 plus R2 times R2 divided by R1. So now we're into the algebra phase here, which is, that's fine. We can do some algebra. All right, so I'm gonna multiply this through. So my R1 will cancel. So over here I'll get R2 here plus I'll have R2 times R2 divided by R1. Then I'll have RX over here. And then I will subtract RS right there. And I may have made a mistake somewhere, but I think this is how we do it. So if we can sort through all of the algebra here, we'll be in good shape. All right, so let's try and figure this out. Okay. Did we make a mistake somewhere? Here's RX. Okay, so wait a minute. Did I mess? Oh my gosh, I made a mistake up here. This was supposed to be RS, not R2. So this is RS here. Oh my goodness. Oh, this catastrophic algebra mistakes. This should be RS. So this will be RS here. Then we'll have an RS here. So now we'll have RS. Then R1 here. We'll get an R1 over here. So there's R1. Oh gosh, I made a mistake. Okay, so RS. So if I multiply this through, nothing cancels here. Oh, this was my mistake. All right, let's forget that. All right, so RX is equal to R1 times RS divided by R1 plus R2 times RS divided by R1. And then minus, over here, I'll have a minus RS. Oh, and look at that. We've done it. Okay, so this one goes away. This one goes away. Now I've got RS minus RS. And this was an R2. Yeah, that was R2. There's an R2. So the final answer then is RX equals R2 times RS divided by R1. There we go. We've done it, guys. All right. So thanks for watching as I messed up all of the algebra. Okay, guys. Well, that's it for now, guys. I'm going to post a test later, so thanks for staying with me.
Thank you. Like and subscribe down below.